Abhi is our NLSI/Survey Central funded postdoc. He's been with Jack Burns's group at University of Colorado for I believe it's about 2 years right now, and he is going to give an update on the Dark Ages Radio Explorer, otherwise known as DARE. So, Abhi, go ahead.
Thanks, Greg. Good morning, everybody. Today, I will be speaking mainly about this DARE, or the Dark Ages Radio Explorer, and the status update where we are currently at. And this will be followed up by 2 talks, Geraint and Jordan, following different aspects of the experiment. So, to start with, this is the DARE project team. Jack Burns is the PI at University of Colorado Boulder. The deputy PI is Joseph Lazio at JPL. The project is managed by Jill Bauman at NASA Ames. There are a long list of people over here. A few to mention: Rich Bradley at NRAO. Rich Bradley at NRAO, who is mainly in charge of designing the antenna and testing some of the equipments. And there is Judd Bowman, who is also a collaborator, also a PI of Ages, which is a pathfinder to DARE in some sense. Then there is Geraint, myself, Jordan, and also Steve and Abhirup and Jonathan Pritchard are the theoreticians in the group. So I think Justin, Jack, and Steve gave a pretty much overview of the theoretical background of this experiment. Just to sum it up, this is the H1 brightness temperature as we would like to detect. This is one of the models, and DARE will be focusing mainly between 40 and 120 megahertz, which is roughly the redshift range between close to 12 to roughly 35. So that is the DARE window, and the way we kind of parameterize this signal is in terms of these turning points, the B, C, and D, and Jordan will elaborate more on what they are and how to go about it. Just to give a basic standpoint where DARE stands in comparison to other experiments which are also trying to detect similar things. Ages is currently the only instrument which has taken data and actually have a science result, but it operates at a higher frequency between 100 and 200 megahertz. DARE, which is this project, which is between 40 and 120, so we go far below where Ages ends at. There is a bunch of other, the LIDA, there is a poster, I guess, in this forum. Dawn and Bighorns is a Western Australia initiative, and Saras, which is the Indian initiative, again going to be launched. But none of these bottom 4 have any significant operations yet. They have been testing and doing some basic concept designs and stuff like that. So Ages is what DARE takes as the basic pathfinder. So we incorporate the lessons learned from Ages and how difficult these low frequency radio experiments are from the ground. So we move on. So Dark Ages in a slide, what it is. So this is the DARE instrument in concept at least. And yeah, okay. This is how it should look like when it is finally built and flown. So it will basically be launched from the Earth, and it will go around the Moon and settled out in a roughly 200-kilometer orbit above the Moon. This is still not decided yet. We are still finalizing what orbit should it be on, depending on stability. And also, this most important thing is this radio quiet zone shown in the black, which is basically where the Moon shields all the radio frequency interference at this low radio frequencies coming from the Earth. And we have recently done some preliminary studies of how wide is this radio quiet zone, and it depends definitely on the altitude above the far side, but we think we are pretty okay, and we can take sufficient data in a 3-year lifetime mission, being at 100 between 100 and 300, 400 kilometer orbit. So the final thing is still to be decided. So going on. Okay. So okay. Just to give a sense why this radio frequency interference is so important. This is the data taken by AGES, which is above 100 megahertz, and the situation is a little bit worse, below 100. That is clear from our data, which I will show at the end. And you see that this, even at the Western Australia, which is one of the remote sites in the Earth, you still see this heavy interference, which basically consumes much of the bandwidth of the operation. In fact, one of these Murchison wide field array, which is another interferometer going to taking data to detect fluctuations in the H1 signals, have detected reflections of the Earth-based RFI from the moon, and they have put it out in this 2012 paper, and which basically says even in the remote site you will be able to see the reflections from the moon when it is up. So, yeah. So also there will be reflections from the space debris which is floating around the Earth, and so even a remote site will not be absolutely clean from RFI. On the other hand, if you go to moon, this is a very old data taken by Radio Astronomy Explorer in 1973, and you see all these spikes and everything, which is when the Explorer was on the near side, and when it went to the far side, it's completely very quiet. So that's the radio quiet zone, which I shown in the previous slides. So going on. So what is DARE status? It was, as you might know, DARE was first proposed as the Explorer Class mission in February 2012. The mission was not accepted for Phase A study, but got very high FRA ratings, so we just missed. Since then, DARE engineering prototype has been built by NRO and JPL. The first generation testing was done between February and March 2012 in Green Bank, where we basically assembled the entire instrument, put it out in the field, checked some very first order stuff, and things worked. So we deployed the same instrument back in Western Australia in the radio quiet atmosphere. And in November 2012, we actually upgraded our digital spectrometer with a much more advanced. That's why that is a second generation field test, and third generation is coming up in Green Bank again in August, late August 2013. So in a few weeks from now, where we have an improved instrument design and also the receiver, and which will be very critical. So all the results from these three field tests will be very critical to the proposed DARE for a small to medium Explorer class mission in late 2014. Okay, so this is the DARE antenna, which you already seen. This is the biconical dipole, which is hosted on the top, and instead of the traditional ground screen, which is more continuous, we will be using this deployable antenna radials, which are far, very much mimic the actual continuous ground screen at this low frequencies, essentially. This is a rough beam pattern. There has roughly a 55-degree full width half maxima beam, primary beam, and this is the antenna response function for the very preliminary design, but we will be upgrading it to a new one very soon in the August field test. So DARE prototype, basically all the components separately, the antenna, the balun assembly, the receiver, and the digital spectrometer individually have very high technology readiness level, but it was never demonstrated before that the combined instrument has a TRL greater than or equal to 6. So that's what we are doing in this field test. So this is some pictures from the first Green Bank test. We had some issues initially, but then we sorted out. You see the traditional Green Bank single dish, the Green Bank dish 100 meter in the back, and the new generation radio instrument in the front. This is how the DARE instrument looks like in the field. It's closed in the styrofoam box. Then the cables down through in the heart. Unfortunately, we cannot show that. This is the heart. This is that heart where the receiver and the computer stays. Similarly, in Western Australia, it was deployed in March, but then in November, it went through a bit of upgrade of the digital spectrometer. So that's where their instrument sits, which is very near to the edges where this should be where it is. Moving on, just to give you a glimpse of the calibration. So it's basically you have two stages, the on and off. When the on is when it's connected to the antenna, and off is when it's connected to a 50 ohm load. This is very critical for calibrating the instrument. So initially we did a very naive calibration and then kind of normalize it with the instrument, the antenna response. But now we are going forward to make a more robust, detailed lab-based modeling, and that will be a much improvement on the previous one. Just to show, this is the initial science result from Green Bank. This is the calibrated spectra, and it pretty much matches with what the expectation of the characteristic synchrotron spectra is, 2.7, which is 2.5 is the expected one, which is pretty close. But now, if you look deeply, there is this FM band, which is ever present in Green Bank at least. And if you compare with the sine signal, the turning point D will be never observed if we have the instrument in Green Bank. And then you see some effects from the ionosphere, which is also more clear from this slide, where this is much more recent data from Western Australia in July 9. I just chose this date because it's on birthday. So you see the vertical stripes, which is the RFI, and you see this horizontal stripe, which is basically when the solar storm happens, some ionospheric irregularities happen, the entire bands get slashed, and you see the galaxy coming up in the front. So that's pretty much where we are. Just to sum it up, not only we are doing this gradual improvement in the field test, going from first, second to the third generation, but also it is also accompanied with rigorous laboratory tests in controlled environments done by NRAO, ASU, the Arizona State University, and the JPL. So much of work has been done till so far, and we are progressing pretty good. Just to mention that initial field test data show very strong effect of the RFI and also the ionosphere. And these are the major challenges for any DARE-like ground-based experiments. And that's a good point to stop, where Karen will pick up mostly. So thanks, Greg. Thanks, everybody.
Thanks, Abhi. Very nice. I want to say happy belated birthday.
Thanks.
Let's see. I don't see any questions online right now. But let me just ask you one. What do you see as the biggest remaining challenge in balancing everything? You guys have done a tremendous amount of work, of course, in the last 2 or 3 years. But what's the biggest hurdle that you have before you repropose next year?
I think we are making the instrument more and more sensitive and try to meet the mission science goal, like sensitivity which is required for their instrument to actually detect the signal. And we have a path forward, and we are trying through this gradual field test and the lab-based tests, we are sorting out one hurdle after the other. So so far things are looking smooth, but yeah. So I think we have a plan forward.
Excellent, excellent. Well, great, and that's excellent. And we've been really proud to be able to support you in this work from NLSI Central as well. So it's one of the things. Yeah. One of the things that I'll relate back to actually the first days of the Astrobiology Institute, the very first virtual institute, when Dan Golden came to Ames to welcome our first director, Nobelist Baruch Blumberg. He said there's a single criterion for success of this new institute, and that's missions. And so I think you guys are doing a great job there and having such a successful mission, and wish you luck in the next round of proposals. So thanks again.
Thank you. Thanks again for your support.